Alright, hello everyone. Today we will be doing some lab maintenance. So I'll work on this Keithley 182M nanovoltmeter and Fluke 5720 calibrator. Let's check the sound check. Hopefully this time sound is a little bit better. Okay. So the special part about this 182M, M means modified, most likely. Special about it is floating front end, even if the meter is off, but that means it have to be powered at all times, and for that small cell battery used inside the meter. So the battery is like this, 9-volt battery. It's typical to find in usual handheld DMMs, but as with any battery, it will deplete the charge over time, and last time I replaced the battery inside the meter was at least a year ago. So now what I'll have to do is to open this meter and replace the battery. Hopefully sound and video quality is good and we can proceed with the repair, or I would say rather maintenance. And to show that it's still working fine, I'll remove this Keithley 1488 low thermal short and connect small portable precision reference or precision source, which is sitting right in here. It's Ian Johnston's device. You can go to www.ianjohnstons.com and find more details about this little cute device. So it's essentially LM399 voltage reference and precision DAC in one compact package with the screen and simple to use UI. So you can source any voltage up to 10 volts with the resolution down to 5.5 digits. Very handy to use at lab, and even it may be not as capable as expensive full-blown calibrator, it's actually quite capable for their money. So Ian sent me one of these prototypes for a test, and I will be releasing the review of it hopefully this month. So to confirm that the meter is still functional, we can connect the input and source some voltage and see what happens. So you can see some voltage jumping around. This is the lowest range, 3 millivolts, and I can set 1 millivolt. So we have some reading. And it's around 1 millivolt, but not very close. So we can test the battery after we remove the old one to check if it's still okay or not. But so far everything looks okay. We can go 30 millivolt range, source 10 millivolts, 20, 30, and then we can go next range 300, so 200, 100, 200, 300, no problem, still looks working good. And then 0 will go down to, this is 1 microvolt, and down would have some noise jumping around. This meter was replaced by more modern Keithley 2182, which are also far more expensive. And this is with the short. And the predecessor of this instrument is Keithley 181. So they are very similar in design. And use, though, like older meters like this one, use this special military grade connector, which is quite expensive and hard to find. And newer meters use custom key Lemo FVN1 series 4-pin connector. Alright, let's get to it. And disassembled exactly the same way as many other Keithley instruments in this form factor. Remove 2 screws from the rear bezel and remove the screw from the bottom, and then it should be good to go. Few more threads. Sorry for the sound. And here we are. As you can see, there is analog section right in here. So this is digital board and analog section in here. And the battery that powers the front end is mounted right outside, so it's very easy to replace. Not very invasive to the instrument. And on the digital side, we can see the main processor. It's Motorola 68000 and some firmware ROMs in here. Then some RAM, these 2 chips. This is analog output, and this is the GPIB interface chipset. And that's it. And there is connector to the front panel and connector to the analog board. And then if you can have a peek in there, it's kind of hard to see, but there are 2 transformers for good isolation from mains noise, and whole analog section is shielded with own metal cover. But we will not touch that. All we need to do is to remove the battery There we go. And wiggle it around. This is factory modification, it's not something done by any user. So you can see even the cover special have the placement for the battery, and I don't want to cut this zip tie. And there should be a way to get the battery out without... Yeah, there we go. So we can check the battery voltage. It's probably still enough juice, but just to be sure, we'll replace with a new one. Let me find DMM. Good old Fluke 87. Well, the battery is still very good, 924 volts, and don't mind the polarity, doesn't really matter. And the new battery is 969. I'll just put the new battery in. Let's connect it first. There we go. And now it's in place, and everybody happy. So that's it for this instrument. Let's put the cover back in. There is no fan in here, and it runs quite warm, but that's not a problem. It's designed this way. And the battery keeps the front end energized at all times, so even if when the meter is turned off, the front end input current and input impedance does not change and stay very high. So the instrument, even when it's not powered on, does not affect whatever circuit you have connected it to. A little bit tricky to get this cover back in because of all the latches. There we go. Now we can put the rear bezel. Standard 182 meter, Keithley 182, does not have this option, does not have the battery. So this is only specific for 182-M modification. I had this instrument for quite a while, and actually only recently I replaced it with modern 2182A. So actually, if anybody want this Keithley 182 nanovoltmeter, then I could probably part with it and sell it for a decent price. And of course I could do full calibration for it, all ranges, all functions, and it would come with the report. Now we can power on and see that everything is still okay. So it may take a little bit of time to warm up. The next thing on the maintenance list is much more involving, and we will have to take apart almost the whole instrument to do what I have planned. So let's set, let's say, 2 millivolts. And we can play with some settings. Integration time 100 milliseconds, that's the most this meter can do. Display resolution can go up to 6.5 digits. Reading relative, in case one need that. Output, that's the output for rear BNC connector. So in this function, DMM will use input, amplify it to specific gain, which we can set in there, and then provide isolated output on the rear. Could be useful for like digitize experiments. Yeah, and then rest is GPIB address and set up, save some profiles. So we can set 0 again, then do the relative 0, like apply some filtering so it doesn't jump around as much. Then do the relative 0, and we can do 1 millivolt, and we get about the same. So we can leave this instrument sitting aside, powered on, and we'll do more tests in future. But for now, we can just double check that all the ranges are fine. So 10, 20, 30, 100, 200, 300. Oh, that's 1 volt, 2 volts, 3, 4, 5, 6, 7, 8, 9, and 10 volts. We can do also opposite polarity. So this is 9, 999, 86. And then swap the terminals. And it's almost the same. Ideally, you would see the same value in either polarity. That would mean you don't have parasitics from cabling and connections. But you would also need to wait a longer time to make sure everything settles down. Okay, that's good for this one. Let's move it aside. And because for the calibrator we need much more space. Okay. Now this is the beast. It's quite heavy. And what I'll need to do is replace the motherboard. I have the fresh motherboard, this one, which I want to be installed in the unit, and it would need some minor repair first, because one of the spade connectors, I can probably show right there, like the brown wire, come loose, so we'll have to restore that and clean up this board a little bit, and then install some relays and take everything out from current assembly, remove the original board, put the new one in, so it would take us quite a while. There are some random issues, so I want to replace the motherboard to try to figure out if it's issue from the motherboard or from the modules inside the calibrator, to allow me to narrow down where the source of the all problems. And random issues are involving sometimes it passes self-calibration, sometimes it doesn't, and it's not very reliable. But when it operates, it works fine for days, unless you power cycle it or do some specific settings. But obviously it's not very trustworthy if it sometimes works, sometimes doesn't. Most of the problems like that caused by mechanical issues, like bad relay or bad contacts. If it would be something with electronics, like damaged op-amp or resistor or some transistor, then it would be always not working. This is how 5720 looks inside. Other than this cover and that cover are not original, they are do-it-yourself kind of covers, because I bought everything you see in this calibrator as separate parts and not as a factory unit. Okay, hopefully the light is okay. And these calibrators, even used or broken, can be quite expensive. Like enough to buy some decent used car. I spent multiple years to assemble first one and now the second one. And there are a lot of modules inside, and I can go each one of them one by one if I have enough cables. Yeah, that should do it. So we have this is power supply card, left from, if we start from left to right, this is power supply card. This is another power supply card with the filters and also interface between the earth referenced digital part and digital controller for the analog part. Here is the one of the power amplifier power supplies and also power amplifier circuits. Here is the high voltage board for and high current for 2.2 amps and for 1000 volt output. Here is the another high voltage assembly. This is high voltage transformer and with switching and other analog circuitry. This is A13 oscillator output board for the AC functions. Here is AC sensor board, which is required for calibration and for conversion DC to AC transfer. Here is the main heart of the calibrator, deck ref deck. It contains dual LT-FLU ceramic hybrid and all the main ADC nanometer and precision deck that is generating 22 volts, 11 volts ranges and based functions for the artifact calibration. Here is the resistance board, and here is the resistance calibration board. Here is the this is A8 switching matrix board. Have a lot of relays to commutate signals around the calibrator. And then this board right here is AC oscillator together with the current function board. And that board is repaired. You can see the bodge wires and bodge resistors, because original hybrid on this board was damaged. It was just drifting all the time. So I replaced it with this hacked solution for the time being, but actually I already bought the replacement board with the original network, but didn't receive it yet. So we need our friend Todd to help with that. So hopefully within this year I can get this board replaced as well. And you can see some foam I left behind. This is to avoid the boards shifting during transit. So we can remove all that, because we will be removing all the modules anyway. And we can start from the first one. So I can show this is the A7. Lot of relays. This is A8. Even more relays. And on the rear side, is the ohm calibration board. So it's also have all the circuitry required for the resistance function calibration, but also 1 ohm and 1.9 wire wound resistors. They are sitting right here in this board. And then the primary reference for all the resistance functions for auto calibration is this hybrid. It contains 10 kilo ohm output resistance network. Then the next board is working resistant board. So here is this from the back. This is a shield for the thermal equalization. And here are 3 main networks, which used to generate all the decayed resistances from 10 ohm up to 100 mega ohm. And 100 mega ohm is separate resistor right there, made by KDOC on this board, TF656R, and it's made in 1991. And there are some read relays and also many standard latching relays to select which resistor is used for the output function. The next one is a reference deck. We have dual shields everywhere. I actually have multiple of these boards, and they are very important for the calibrator performance. Actually, I didn't like that, so I'll have to take a look on inside to make sure everything is fine. I'll leave this board aside for now. This is A12. This is the most important board for AC voltage function. There is a plastic cup under here to protect the thermal sensors from the airflow. So the conversion between DC and AC can be done in a stable and precise way. I also didn't replace any tantalum capacitors in this board, so that will be another thing to do. Then we have A13. This is oscillator output board. I have a bunch of power transistors. I have somebody's labels, fail, fails artifact, but actually I don't have a problem with this after a repair. Now this is one of the bad boards, so I'll have to either replace it eventually. Like all the parts are okay except this hybrid, which have a crack, so the heater doesn't work on it. Otherwise it's a working board, only need to replace this hybrid. And this one is kind of hacked together. This is not original stuff, so I didn't have the metal cover that goes originally, so I just makeshift cardboard piece to direct the airflow like it's supposed to go. But now I have actually a replacement board, damaged board, but with a good cover, so I'll take the cover from that board and put on this one. Otherwise it's normal functioning board. Now we need to release two screws that hold high voltage transformer down to the chassis. Actually we need to release 3 screws, one on the side. Okay. Now we can release the board. So we have the shield and large heavy transformer and some of the auxiliary stuff. Now we have to remove these 2 modules. Oops, somebody fall off inside. So that's there is the CPU. You can see the pads on the back. So this is CPU in here and firmware ROM. And this is the power supply board. I already replaced all the capacitors before, and it's actually one of the repaired boards I used in the previous calibrator. So there is a big hole in here and some bodge wires, but this board worked for me for half a year and didn't cause any issues, so I'm quite confident it should be fine. I can show you the damages. Yeah, there is a see-through hole because I had to cut out all the material and chart PCB to avoid leakage. It was caused by the bad resistor. There were 2, actually 1 on each side, carbon resistor, which failed and heated, and then everything went toasted, damaging the PCB. So there is a nut, and now that removed all the boards inside. We can take a look inside. So there is the fiber interface with the fiber optic cable between the digital and analog parts. We can disconnect that, and we will need to remove the relays from the front. And I would also have to remove the front panel to disconnect the cable. Let's move it other side. And the main output relays are right in here, 3 relays, so I'll have to remove those as well. These are special relays made for this calibrator. They are focus. Made by company American Zettler, and part number is AZ421217200. So I bet they cost pretty good money, around 25 USD for one relay, and the standard they are standard size but not standard connector location. This relay is often called R10, and the standards have the contacts either here or there or 2 together, but this one have in the middle. So there are 3 of them, same type, inside the calibrator. And now what we can do is remove the bottom cover and remove the front panel and get this motherboard out of the unit. Let me check some comments. Alright, so let's get back to taking this thing apart. It's much lighter now without all the boards sitting in the unit. Now we need to remove the other side. And again, this cover is not original. I have ordered custom aluminum covers with powder paint, and standard covers are white, like white beige color. Obviously these are not standard. It was just easier for me to order custom covers than to try to get the original ones from Fluke. And here we go. This piece of MDF is also not original, obviously. There should be a shield all over the board, which covered this whole section, but I didn't have the shield, so I just put this contraption to avoid the metal case touching any exposed pins on the board. So, okay, sadly we will have to remove that side boards too, because this board cannot be removed without replacing another one, because the boards overlap. Like this is where is one board ends and goes to the second one. So this connector is power delivery between both of the boards, and there is another one right behind this metal cover. And the repair I was doing was this and this. Both of these boards are 6 layers. And we can probably start with removing the front panel. here we are. So you can see there are two cables. This large ribbon cable connects all the digital interface for the front panel, and then all the analog stuff for the outputs, like connectors, cable with the connectors, is right in this assembly. So we'll have to remove the cable, as the cable is soldered directly to the main board. And can also, yeah, I'll need the hex screw for that, screwdriver. Probably 1/4 inch would be the right size. No, too small. Yeah, that's about the right size. So probably we'll wear gloves to avoid contamination on the copper surfaces. And there is a handy label which shows which connector, which cable goes where. It's nice attention to a detail, and for the easier servicing of these expensive instruments. Now if I only could find where did I put my bag of gloves, that would be very good. Here it is. As you can see, all the connections are with the pure tellurium copper without any plating, to provide the lowest EMF errors possible for the precision instrument like this. Even very thin nickel plating, which we often see on the cheap connectors and cables and pins, can ruin their performance. I don't need to remove that one. Oops. I think I'll better get some tools. There are washers and the nuts. They are both made from copper. Come on. Now we need to remove the last one. Now unscrew these two. And now we can release the cable. There we go. Now here is the front panel. Nice and clean. It's very robust design, and vacuum displays are in here, two of them. The keypad feels and works for many years, and then these connectors can be replaced. The posts and the shorting plug between the ground and guard. So this is all fine. We'll take this out. Now we can worry to remove the remaining boards. I did a few mistakes on this cover, so it doesn't really fit with that well. And oh boy, I think I'll have to remove the rear one as well. All right. At least at one side. Just go right off. Yep. put this back in. This is the mains transformer. We don't need to touch that. All we need to do is remove the digital power supply board. So we can have some big capacitors here. And the main processor board. Here they are. And now we can go ahead and remove that board first, then remove this board, then fix the new one, put a new one in, and do the reverse process. I know it's not very entertaining, but this is what I do for hobby. I have more original bits and pieces in my first 5720, so this one is secondary unit which I put from the remaining bits and spare parts, so I didn't put so much attention on this one as the first one. I had even crazy idea to build a third one, but then census come in and that financial exercise wouldn't be very reasonable. Because even to build it from scrap, it's still thousands and thousands. Okay, so we can probably leave this in place. Just remove those screws. Now I still have to remove the rear stuff. Because of this connector, there is a cable going to the back of the panel for the external booster interface. I forgot about that one. So yeah, I was hoping for an easy board replacement, but I actually need to disassemble the whole thing. Okay, board is loose, so let me get to there. Okay, why it doesn't go out? There we go. So there is another board on the back with a bunch of more relays. Relays everywhere. Let's disconnect this cable before I destroy stuff. There we go. Now there is hacked together adapter from this cable to the pins which go to this cable and connect to this port. So I'll need to remove all that to release this black cable. The original cable here didn't have, had this cable completely cut, so I had to make this botch so I can still interface it for the rear PCB. But the new motherboard have the proper termination, proper cable, so that was another reason why I wanted to replace the motherboard. Alright, now that we can release the board, I hope we can try to do so. Put it down. What's going on there? Oh, okay. There is a bracket. And the battery went dead. I need to get some either proper camera or the power supply to power the camera from the mains to prevent this from happening. Okay, we are out. So here is the old motherboard. Finally out. So this board is actually from year 1990 and the new one is from 1992. But they are same revision, same design. So we can retire this board for now and get the new one ready to go in. But before we do that, we need to replace the broken wire on the connector. And here is how that original high voltage cable looked like. So you have the same idea, two terminals and then the wire connected right to those vias. So now we can get this stuff serviced. So there is that brown wire. Let's check on the legend What's the brown wire do? So there are all the nice labels, and brown goes to the sense high. So yeah, that's an important wire. We want that to be fixed. Shouldn't take much time. So the original terminal is still there, just got a little bit bent. We can straighten that out carefully. And then it was crimped and then soldered. So I probably could try to find a similar round connector. And then there was this, I think this is the filter there. So let's cut this one open and see what's inside. Yeah, there is indeed a ferrite core to filter some high frequency EMI. So we can, yeah, you can see there is that ferrite. We can put it back. No big deal. There you have it. And then put a thermal shrink on top of it. Let me find the connector. I think I already see the candidate. It's in my magic box with all the low thermal stuff. Let me show just that. So that's a bunch of lemma connectors. A bunch of adapters. And actually this does not belong here. Some more low thermal connectors. There's a bunch of my secret stash of copper nuts, spade lugs, washers, some binding post, more spade lugs, extra long banana post, some lemma connector, but I think this is what we're looking for. So yeah, this should do it. It's actually bigger than original. But we don't mind. It will do the job. So I'll probably will just crimp. Yeah, it's much bigger than original. And let's should check that it will fit the post. So here is the post. Oh, it fits nice. No problem. So I'll crimp the pin and then solder on top to make sure it stays in place. And then we're good to go. A thermal shrink for that. To put the bead back in place. All right. I think this should be good. Maybe one size bigger. This blue one. A little bit too big. How about this yellow one? Yeah, yellow one will do. Here's our crimper tool. So let's clean up some insulation on the wire. There we go. Now we can put the ferrite in. This is a little bit too tight. Yeah, this is too tight. Yeah, green one is much better. Well, the original connection was crimped and soldered. So if it's good enough for Fluke, then it's good enough for me as well. And it's not like this joint will have a lot of mechanical stress over time. It's pretty much, once it's done, it's done. Then that wire does not go anywhere. There we go. Let's check, make sure. Yeah, that should do. Probably do it, bend it a few times. Yeah, as you can see, the copper exposed. It's always a good sign. And that should do it. Yeah, it looks okay. Now I need a piece of solder. I saw some somewhere nearby. Oh, here it is. So should be easy. Just one simple touch. And that's it. Let it flow inside. Should be okay. Now we need to put the board in place and then start assembling everything together and check a few things in the process. I want to give you clean swipes for around connectors before we go. Nasty. These calibrators are often run for many years without turning off, so when you get the board like this, old board, have all the sort of dust and crud on top of them thanks to the fans in the unit. So I always use some cleaning every time I have a chance to open one of these up. And actually, when I replace the fans, I prefer to put higher speed ones, even they are more noisy, but they would mitigate the problems with the bad thermals over time when everything gets dirty inside. Okay, the rest of the board doesn't look too bad. So we should be good to go. Maybe do a few brushes here. You can see also a big common mode choking across the whole cable, which mounts on the front panel case. Have a little PCB with the mounting holes, so it all can be held in place and secured in the fixed position. Very nice attention to details. Alright, let's put it all back together. Now we want to be careful with all the cables, not to damage them and not to cause more destruction. This one goes right over there. like so. And all this go right over there. Like so. Okay. Everything looks aligned. Let's make sure that yeah. Now the boards are interconnected and we can screw them down. Now there are different screw lengths, so we should look closely which one goes where. Oops. Don't go over there. Nope, wrong screw. Actually, that was the right one. This one short. Okay, this board does not go anywhere. Now we need to fix the remaining stuff. Okay. I think we can put it upside down to connect all the rear stuff. Let's go a little bit further. And turn it all upside down. There we go. Now we need to take care of all the connections in here. And also, yeah, that's all good. And those red relays on the main board are not available. They are custom, made special for Fluke. Justo, that's an interesting name. The reason that some parts are soldered is mostly because either repair or modification, or some parts are hand soldered during the assembly process, like some connectors. That is normal. So what I'll need to do is to connect this PCB, and this metal work is not original, and we need to put this one in there because that's how it goes. Can I try both of them? That's probably not a very good idea. There we go. So this interface board stays like that. And that's how we will put it. Now I need 2 screws. For this high voltage cable. This cable carry 1000 volts AC. So it's made especially to have lowest capacitance and good isolation. So wires inside this thick black cable are actually very thin inside, and it's not flexible at all. Alright, and now this is red and that is black. And the thermal EMF is not important, so we can use the nickel-plated screw, nickel-plated nut in there, because it's only for AC voltage. There you see, much better view. Okay, it's all nice. Okay, let's connect the cables and put this board back in. I think this should go this way. Now I'll hack together to put it in place. Something like that. This is also not original part. Just something botched together. And held by these two nuts. Let's hope this all works. Now we can screw this rear panel back. Так. Okay. And to put on other side. There we go. Original calibrator have the filter in here with the metal mesh, but I don't really care. So there is no filter here. Now we can connect the front panel, but I think first I will put the rear cover, bottom cover. So we don't damage the PCB or anything on the back when we mess stuff around. And also there are spacers in here. Let me show you these spacers. They are silicone rubber pins, so they will prevent any metal pins from touching the cover. And also cover from one side doesn't have any holes, and from other side have the vent holes. So the vent holes are an orientation towards the analog output section. So it's actually a very nice thing, because all the hot air will be exhausted from only one side on the calibrator. There we go. That's good enough. I'll put just a few screws in first. I think there were different screws in there. Yeah, that's more like it. Let's remove these ones. They don't belong. All right. Now we can start assembling the stuff. Connect the fiber optic cable. It's right there. There we go. Now we can get the front panel. Okay, let's do all the wiring for the posts. So now we need to follow the color codes. Yeah, probably I should fix the cable in place. There we go. Should be good view for all the low thermal cable aficionados. So let's do blue. Blue. Okay, this blue goes to the LO together with gray. So we have gray. No, that's not gray. This is gray. Let's get blue one in place. There you go. And probably do yellow first because it's down there. Yellow. Yellow is the current one. We can do it here and forget about it. Put a washer. Oops. Where are you going? And the nut. Oh boy. Now we can do the gray, blue, gray, blue, and blue. Hold on, gray, blue. No, blue goes to there. Gray, blue shield, and green. Yes. No. Blue shield. So here is blue shield. Looks like somebody stepped on it. It's all crooked. Doesn't really even go. I don't like that. Need to straighten it out a little. I'm not sure how we'll do it. The perks of buying stuff on eBay. Well, it kind of goes, so yeah, okay. Let's put a washer. There we go. So gray, blue shield, and green shield. And we leave this one. Green shield, yes. Another washer and the nut. This is our LO post. We have 3 wires coming to the one post. Now we have blue and green. Go to that terminal. It's the high. And this is kind of 2 10s. I don't like that. Let's get some of our cable back in place. Oops. Now you don't go anywhere. Okay. Now the guard goes black and overall shield. And where is black? This is black, I guess. And overall shield. Well, that is our overall shield, so there is only black one wire. That one is very easy. Now we have violet and brown shield. Here is violet. And then this is our brown. And this is its shield. Okay. Let's do and then this is just brown, the one that we repaired. Let's try this out of the way. Now I think I'll put 2 additional washers that are left behind to our high and low. Is all the video stream is okay? Sound is okay? Sound check, 1 1. 1 2 3. Anybody still watching? I think everybody is already asleep. Let's get this one out. Okay, great. And here we go. And then this SMA port you see in here, that's for the wideband option. And it connects it's actually bulkhead adapter, type N to SMA. This calibrator does not have the wideband option. I don't plan to put it in. It's 2 additional modules in front of the calibrator. So, but my first calibrator, the primary one, that one does have the wideband option. But here, it's just a pigtail wire. That does not connect to anything on the other side. Yeah, I think I'll just probably leave that one as it is. Okay, I think we're done with cabling. Everything nice and tight, but not too tight because copper is soft and it can be very easily stripped, and then we'll have bigger problems. So now we need to connect everything back together. Let's put the interface cable down there. Okay. Put this SMA cable so it doesn't fly around. And now we can put the front panel. assembly back into the case. There we go. Put a few screws back in. That one didn't go so well. And I'm using the wrong screwdriver. Again. Let me fix that. No, this one is too big. Okay, that's better. Now we can put digital stuff. And put the minimum amount of boards and try to power on and see what happens. This should be fun. Oh wow. I think I shouldn't unscrew that one. Yeah, let's put it back in. Because this frame wasn't very straight, so okay. I screwed this too fast. Let's put this board back in. Sorta kinda there. Good enough for America. Guess these gloves already no use. So let's put some important stuff back into place. And yeah, that's enough. We can power on like this, and calibrator should boot up and show us some messages. I want to put the relay before I do all that. And the relay go right over there. I'll just put it off camera. It's nothing much interesting, right? I show how to remove them, so it's exactly the opposite. And then the bracket to hold them down. Okay. Now we can go ahead and apply some power and check if it's still happy. I guess I need to lift the camera down just a little. The screen on this calibrator is quite dim. It's still usable. So let's make sure the power switch is off. Now it is. Connecting mains. And turn on. Okay, we hear some fans working. And the stuff is booting. Okay, it's booted fine. No blue smoke anywhere. I can show. Let me change the angle. And I can turn off some lights. So it's actually possible to see how it boots. Yeah, probably if I turn off this light, then that should give enough image. There we go. So it booted fine. Now we can start putting boards back and do the testing. Probably this would be a good angle. So the next board is this guy, and I'll need to put the metal cover on it. So that's what I'll do right now. I have the same faulty board. This is A16. This board is bad. And what is bad is very obvious. Let me find. This chip supposed to look like this one, but it have something blown up, and it's missing actual piece of the top case. And also there are some parts removed, like you can see those 3 holes in there. They are supposed to be transistors there. So this will be another project for repair, this board. But now we can just take this shield off and put it on this one. All we need to do is to remove some screws and it will come right off. And off she comes. So this vent have extra shape for the air duct. Actually, the thermal management inside of this calibrator is very important for its performance. So actually critical part of the circuit, like for example there is an amplifier in here under the plastic cover, which have its own separate oven to stabilize the temperature for the critical important stuff. And there are multiple ovens like that on the various assemblies and modules, especially the reference deck. It have no less than 2 of them, and they all kept at the same temperature, no matter what the ambient is, how dirty is the fan, and stuff like that. So the calibrator can maintain its performance, even though it can be used in the field where the different ambient temperature, different environment, but maintain its calibration and accuracy. There we go. So most of its power, it's actually wasted into the linear power supplies and these ovens that run all the time, and not actually the analog like socket function. There we go. Oops. I need to remove this cover. That's better. And there were 2 screws. There you go. All the pins are good. I think we can put this board back in. I missed the hole. There are slots to guide the board in the right place. Now we are in place. Now we can put the rest of the boards. It's actually better to put this one first. Okay. Now it's in place. Doesn't go anywhere. Alright, next is A13, A12. Now the main ref deck, and I actually wanted to take this one apart to take a look that make sure it's all good. So this will be an interesting one, but I need some space, probably right over here. That should do it. So I need to remove one screw. This board is the heart of the calibrator, and it's very easy to damage. So I just want to remove the cover and to see that the hybrids are okay. And measure the oven. So their oven are okay too. So we can measure now. It's the corner pin. And hopefully you can see the DMM. Yep. Should be 42 ohms or so. So let's make sure of that. I think that's not the right pin. Let's check another one for sure. Okay, that's the good one. There we go. That's the voltage reference. Right there you can see, let me zoom in, focus. There you go. That's where all the magic happens, and that's why these calibrators are still cost like a car, even today, when they are not serviced anymore by Fluke. That's the money shot. 2 of linear technology, LTFLU, Buried Zener's ref chips, ref amp, and the resistor networks, that ceramic chip in the between of them, and also the whole thing is heated to the constant temperature. You can see there is a resistor and the battery is out. On the most interesting part. I guess that's a sign of live stream to be finished soon, relatively, so we still can go for maybe 20 or so minutes. So let me check which pins does it correspond to. Looks undamaged, so that's a relief. And yeah, it looks okay to me. Yeah, and the heater goes to the pin number 2 and 4, I believe. I mean two from each side. So I'll put carefully cover back in. There we go. Should be this guy and this guy. Yep, 28 ohms. I think that's okay. So there is still good connection. So we can put the board back together. Now we need to put the screw back in. All the pins are looking good. And we can put it back into the unit. and rest of the boards. A10 board. A9. Where is A9? It's over there. Now we have phase A8. I think this board giving me troubles, but I will also have another replacement when Todd will find time to send it to me. Then I'll be doing some more testing, and then my bodge wired A7. Okay, now calibrator is full. We can turn on and do the self-test. Let me turn it on, and probably I'll connect something to the DMM so we can actually check quickly that there is correct output. Right here, you can see it. Let me fetch the cable. Let's turn it on. We hear some relays click. Starting up. I'll connect the voltage. So high and low. Of course, we don't care. Let's source 10 volts. And 10 volts there is. Oh, and my DMM needs a new battery. So I'll not mess with the backlight. 1 volt. There is 1 volt, 100 millivolts. 100 millivolts. We can do 10 millivolts. And then we can do 100 volts. There is 100. We can do 200. We can do 500. There is our 500. Looking good. We can try. Let's try some AC voltage. Let's do 10 volts, 60 hertz. 10 volts, 60 hertz. And change to AC voltage. Operate. There is our 10 volts, 60 hertz. We can do 100 volts. Same frequency. operate. That's 100, 250, 250. Looking good. We can try some current. Let's do we can try 10 milliamps DC. So output normal, okay. Current works. 100 microamp. My bad, 100 microamp. DC. Yes, okay. Let's do 100 Hertz. AC. Okay. 100 microamps. We can try some resistance. Let's do with a short. 2-wire compensation on. Operate. That's pretty much close to the zero. We can do 100 ohms. 100 ohms, okay. 1K. 1K. 10K. 10K, no problems. 100 kilo ohms. Cannot use 2-wire compensation, okay. No problem. 100 kilo ohm. There is 10 mega ohm. 10 mega ohm, no issues. So we can try self-test. Let me zoom in so you can see. Also, I run this for calibrator at, let me show, instrument configuration, show installed hardware. So this calibrator runs special firmware. There you are. LAP, that means it's 5700 EP version, and in guard is B, model 5700, but actually all the specifications and everything is the same as 5720. It's just to outline that calibrators which are upgraded from 5700 to 5720 hardware, but still remain with 5700 CPU and front panel, they would have this special firmware. So, but all the like GPIB programming, all the specs, all the functions exactly the same as 5720. And actual hardware is mixed in here, but we will all be bringing it to 5720 version later this year. All right, so we can do the self-test and see if there are any errors. I expect some errors. So, because I know that there was some issues with one of the boards, switch metrics board, and it didn't always work reliably. So I would expect those errors to stay, but let's see. And also probably the heater error will be reported on the A15 board. And I got this firmware from a friend, so it's always good to post the stuff like I do on website xdevs.com, and people all over the world contact me, and sometimes they ask for some suggestion or consulting, and sometimes they provide me with some goodies like the firmware for calibrator like this. So we help each other, and this is how the great community in metrology section of EV blog operating. And yeah, just Ask nicely, and then sometimes you get what you ask for. Okay, A11 12 DC range fault. This is a new one. I didn't see this one before. This is an interesting error. A11 is the one board that we just took apart to take a look. Let's continue. It could be because the unit is not warmed up. So these usually need like few hours to get all the oven temperatures and everything to the temperature, to the right operation conditions. ADC, amp output noise, okay. And output offset. I guess there is some problem with that board probably. I often get A8 relay failure on this test, not sure, but it doesn't happen all the time. Actually, I'm going to try, after I finish the stream, I'll try my other deck boards to check if there is same issue reported as this one. I can show two other ones. They're actually different levels and different revisions. Okay, more errors. A11, we saw this one, I think. Continue. A8 0 amp low noise fault. Low offset, that's a lot of errors. 0 amp. So I have this one. It says the original couldn't estimate 11 or 22 volts gain, 28, 22. So we have that one to try. Sorry about the noise. And I also have this one. This is 5700 series board. And this is the one I used very first original in the first calibrator. This board should be fine. And yeah, there are multiple of them. And we're still getting the same 2807 error, whatever that means. Find a good settings, so yeah. There you go. Yeah, it doesn't look very happy. I actually remember I stole a hybrid out of one of these boards, so I better check before I install them into the instrument. This one is okay. Yeah, that's way too many errors. Yeah, I guess I can try this board. Let's turn off everything and swap the board. There are a few secrets about servicing these calibrators, and I happen to learn them by practice and spending a lot of time. And it's a shame because Fluke does not service them anymore. So even if you want to do this as a business, I mean, if you have a calibrator and you need to have it in order and something wrong happens with it, then you are on your own, or you need to spend a lot of money for an upgrade to the modern 5730, which is 90% is the same instrument, but with even the most of the specifications are exactly the same, but have the nice and fancy front panel and stuff like that. But actually in the core it's the same instrument. Oops. Let's see which this one goes. We can connect the, check that the voltage is out, output is still there. Of course it will be now very different value because the calibration is between this board and that board is very different, but we still need to check that the output is there, and that would help if I switch to the voltage. Yep, voltage output there. It's okay. We can probably run it for a few minutes and then run the self-test again. But I remember I put this board into my other calibrator and it was all fine. So, that would be an interesting topic to cover some other time. Let's do self-test run. Well, this works the best. Auto accept, huh? Well, hopefully you covered the shipping at least, because these are heavy. I think that about now we should start getting errors. Oh wow, this stream already goes for 3 hours. I guess that should wrap up and finish soon. So if somebody have some specific question or some suggestion for the next video, then this would be a good time to ask. Let me see what's inside of that board. Oop. This one does not even have a screw in it. And I think this is the one where I stole the hybrid. Oh, come on. No, hybrid's still here. Huh. So I must have then another board, other than these two. Okay, there is an error which says, surprise, surprise, 5700 not warmed up. Yeah, that's okay, I know. Let's continue. So let's see what's going on here. Okay. So this board is 5720, but but it's older one. Okay. Oh, okay, I think this is the one I got, the latest one. It's made in 1989, so it's not as fresh. And I want to see what's in here. AA relay fault, okay. I know that one. Let's continue. Doesn't throw any of the A11 errors, so that's a good sign, I guess. Okay, there are some bodge wires. I think this board, I never tested this one. So yeah, it could be interesting. to try. Let me see, the heater is okay. Okay, so we can test this one too. Sometimes it's tricky because some of the issues would be, like for example, it would say like there is error right now on A7, but this issue could be caused by some other board which affecting the A7 operation during diagnostics, and then it would throw the first error which it catches, but it may not be the right direction to troubleshoot. There is a question, do I ever use old-fashioned 720A or other KVD? Well, I used 720 before it, well, it was working sometime after repair, but then something else broke in it, and I never used it since. And then I got, there are a lot of A7 issues, okay. And actually I bought a second 720A, hopefully fixing, at least making 1 out of 2. And I still have them, so I didn't do anything with them. And they are, I can show, they are sitting right over there. One with removed cover and one with cover on. So maybe we can do a video about 720A, but it would be even more boring one than this one. So we'll see. It is a little bit overexposed. I don't have the right studio lights right now and don't even have the right spot. I'm still rearranging the lab, and hopefully by the end of the month I'll have much better layout for videos and much better quality for the lighting as well. So sorry about the poor quality for now, but I figured it could be useful to do at least this kind of stream instead of doing nothing. I mean, online. I like the relays, how they click like when it goes through the testing and calibration. And after like running this 400 times, you kind of hear when something goes wrong and some other issues, then you would hear the wrong relays click. I didn't see this issue before. That's interesting. It's probably because of the current assembly is unhappy for whatever reason. We really need our Todd friend support. Wow, that's a new one. Incorrect PA input. Never see that one before. Yeah, I know this error because of the broken heater. Funny part that I don't really care about that because I wouldn't even use this calibrator for high voltage range, but I need to have those assemblies in for the 2.2 amp current range. High voltage analog. Looks like much less errors than with that board. I also need to replace few capacitors in there. Yeah, okay. On the older boards, just to make sure everything is fine. I don't like to run those old capacitors in the instrument like this, which is supposed to run 24/7 without immediate supervision. Okay, that's the end of the test. This just says that A5, A6 wideband, here 2 assemblies, not present, so it's not an error. And that's it. Diagnostic is done. So we can put this board in and try again. Or put this board in that I never tested. So what do you guys think? One last test. What should we do? Put this one back in to see if the same errors come back, or try untested board. What's the option? What would it be? Come on, people. Say, what should I do? Or we could end the stream right now. The next live stream would probably about new exciting instrument, which hopefully I'll get soon for review, and that will be a lot of challenges, but a lot of interesting results as well. So I'm really looking forward for that. And I actually wanted to have this second calibrator in order so I could do more testing at the same amount of time. Alright, since nobody gives any suggestion, I'll just try this board real quick, and that would be the end of it. Probably I should put some cover on, so I have some time to warm up. I think right about now should throw some errors. Or not. With these guys you never know. Sometimes they like to cooperate, sometimes they don't. I have probably enough boards to build like half of the third one, and those boards are just spares, whatever left behind. Okay, I don't think this is very interesting, so let's call it a day, and that's it for now. If you want more information and more stuff about metrology and high-end test equipment, you can always visit my website, xdevs.com, or talk to a community at EV blog forum in metrology section. There are a lot of great people around there, and everybody playing with different stuff, so it's always a nice learning experience to hang around and read some threads in there. Thank you everyone for watching, and until next time.